Hello everybody. So we're going to have two video lectures on what we're going to do next with the monocrators data. So the first one is just an overview of the new sheet. So here's the old monocrators data. Here's the tab that shows the data. Here are the charts that we made, or at least some of them: magnesium versus calcium, silicon versus calcium. Down here at the bottom in the new sheet, you'll see something called modeling sheet. And so that's the part that's new. And here, if you've watched the other video lectures on partition coefficients and bulk distribution coefficients, that's what this stuff relates to. So here are the partition coefficients. So earlier we looked in the example at the partitioning of magnesium in olivine and plagioclase. There are some different values than what we saw in the examples, but they're pretty close. So olivine has value greater than 1. I'm using 6.5 here for magnesium because magnesium is compatible in olivine, and I have 0.04 for plagioclase because it's incompatible. But we have a lot of other elements to look at: silicon, titanium, aluminum, sodium, potassium, etc. And so we have partition coefficients for all these phases: olivine, plag, clinopyroxene, magnetite, apatite, hornblende, orthopyroxene, and garnet. So these are from experimental studies or observed mineral melt pairs. So this is something that mostly people do from experiment. Down here are the mineral proportions. Remember, we talked about these XJ. So in this case here, I'm assuming that we have crystals that are 50% olivine, 30% plag, and 20% clinopyroxene. You can change these to be anything you like so long as the sum is 1. So let's say I want a little bit less clinopyroxene. I can make that 0.1, but that drops the sum down to 0.9, so I have to increase something else, maybe the amount of plagioclase. Or maybe I want to increase the amount of amphibole. Maybe I want 20% amphibole, but now I've got a sum that's too large, and so we would have to decrease something else. Maybe the olivine goes down to 0.3. So you can have any number of mineral proportions that you like, so long as the sum is 1. Now, so the way this spreadsheet is set up is that this calculation is already done for you. The other thing that's done for you are the bulk distribution coefficients. So in a couple of the videos, I showed you how these bulk distribution coefficients are calculated. So notice that, for example, the bulk distribution coefficient for magnesium here is about 3.8. If I increase the olivine, let's say I make it 0.6, now that makes this sum too high, 1.3, so I'm going to make this 0.1. Notice that the D for magnesium went up to 5.74. That's because magnesium likes to go into olivine, so the bigger the olivine fraction, then the bigger the magnesium, the higher the value for the D magnesium. And of course, I still want this to be equal to 1, so I have to decrease something else over here. Or I can make the olivine component very low. I'll just increase the plagioclase content, and I get a lower value for magnesium. Now, all of these, if you watch this video again, all of these values will change. So I've done these calculations for you. Just to give you an example, this D for magnesium, if we click on that, you'll see it's the sum of the weight of all these multiplied by their partition coefficients. If we do the same thing for aluminum, take a look at this equation. It's the mineral proportions multiplied by the aluminum partition coefficients. So we're going to use these in the next video. I'm going to show you how to use these to develop a model. Now that model is going to involve looking at a starting composition and melt fraction. And we're going to introduce that in the next video so that this one is not too long.